Our story begins billions of years ago. Imagine a vast, dark cloud in space. This wasn't an ordinary cloud, it was a nebula, a giant cloud of gas and dust. This particular nebula, the one destined to become our solar system, was mostly hydrogen and helium. These are the lightest elements. They were the first elements to form after the Big Bang. The solar nebula was not alone. Space is filled with these giant clouds of gas and dust. They are the birthplaces of stars and planets. Our solar nebula was just one of many, but this is the story of our cosmic home. So let's focus on this particular cloud of gas and dust. This cloud was huge, it was light years across, it was also very cold, and it was spinning slowly. But something was about to happen, something that would change everything. Gravity is a force that pulls things together. It's an invisible hand that governs the motion of celestial bodies, from the smallest particles to the largest galaxies. The more massive an object, the stronger its gravity. This is why massive planets and stars have such a profound influence on their surroundings. In the vastness of space, gravity is a sculptor. It molds and shapes the very fabric of the cosmos, creating intricate structures and patterns. It shapes clouds of gas and dust into stars and planets. These clouds, known as nebulae, are the birthplaces of new celestial bodies. And so it was with our solar nebula. This vast cloud of gas and dust was the cradle of our solar system. Gravity started to pull the gas and dust in the nebula towards the center. This inward pull was the beginning of a grand transformation. The cloud began to shrink. As it contracted, the particles within it moved closer together, increasing the gravitational pull. As it shrank, it spun faster and faster. This rotation was a natural consequence of the conservation of angular momentum. The spinning motion caused the cloud to flatten into a disk. This disk would eventually become the plane in which our planets orbit. Imagine a figure skater pulling their arms in as they spin. This is a perfect analogy for what happens in space. They spin faster and faster. The same principle applies to the collapsing nebula. This is conservation of angular momentum. It's a fundamental principle that governs the motion of rotating bodies. The same principle applies to our collapsing nebula. As it spun, it continued to collapse under its own gravity. As the nebula collapsed, it got hotter. The compression of gas and dust generated immense heat. The particles of gas and dust were colliding more and more frequently. This released heat, causing the temperature to rise dramatically. The center of the cloud became incredibly hot and dense. This dense core was the seed of a new star. This was the beginning of our sun. From the collapse of a nebula, a star was born, lighting up the cosmos and giving birth to our solar system. The center of the collapsing nebula became a maelstrom of heat and pressure. Temperatures soared to millions of degrees. The pressure was unimaginable. Under these extreme conditions, something amazing happened. Nuclear fusion began. Nuclear fusion is the process of combining atoms together to create heavier atoms. When hydrogen atoms fuse, they create helium. This process releases enormous amounts of energy. This energy is what makes stars shine. And so, our sun was born. It became a giant ball of hot, glowing gas. It was fueled by nuclear fusion in its core. The sun's gravity held the entire solar system together. It bathed the surrounding disk of gas and dust in light and heat. While the sun was forming at the center, the rest of the solar nebula was not idle. The vast expanse of space surrounding the nascent sun was a dynamic and bustling environment, teeming with activity and potential. The disk of gas and dust was still spinning. This rotation was crucial, as it helped to flatten the nebula into a disk shape, a common feature in the early stages of solar system formation, and it was still being shaped by gravity. Gravitational forces played a pivotal role, pulling material inward, and causing collisions that would eventually lead to the formation of larger bodies. But now, the sun's heat and light were also playing a role. The intense radiation from the young sun began to influence the surrounding material, driving changes in temperature and pressure. Close to the sun, it was too hot for lighter elements like hydrogen and helium to condense. These elements, unable to solidify, remained in a gaseous state and were pushed outward by the solar wind. These elements were pushed out to the outer regions of the disk. This outward migration created a gradient in the composition of the disk, with lighter elements dominating the outer regions. But farther out, it was cooler. In these more distant regions, temperatures were low enough for heavier elements to begin condensing. Here, heavier elements like iron, nickel, and silicon could condense into tiny dust grains. These grains were the first solid materials to form in the young solar system. These dust grains collided with each other. They stuck together. Over time, these collisions led to the formation of larger and larger particles. They formed larger and larger clumps. These clumps, known as planetesimals, were the building blocks of future planets. These clumps continued to grow, attracting more and more dust and gas. The process of accretion allowed these bodies to increase in size and mass. Eventually they became large enough to have their own gravity. This gravitational pull enabled them to attract even more material, further accelerating their growth. These objects, ranging in size from meters to kilometers, are called planetesimals. They varied greatly in size, but all played a crucial role in the formation of planets. They were the building blocks of planets. Through countless collisions and mergers, these planetesimals would eventually coalesce to form the planets we know today. Planetesimals orbited the sun like a swarm of bees. They were constantly colliding with each other. Most collisions were destructive, but some collisions were constructive. When two planetesimals collided at the right speed and angle, they could stick together. Over millions of years, these collisions led to the formation of larger and larger objects. Close to the Sun, where it was hot, only rocky planetesimals could survive. These planetesimals came together to form the inner, rocky planets Mercury, Venus, Earth, and Mars. Farther out, where it was cold, icy planetesimals could also survive. These icy planetesimals came together to form the cores of the giant planets, Jupiter, Saturn, Uranus, and Neptune. Not all planetesimals became planets. Between Mars and Jupiter, the gravitational pull of Jupiter prevented the formation of a large planet. Instead, a region of space called the asteroid belt formed. The asteroid belt is like a cosmic junkyard. It's filled with leftover planetesimals from the early solar system. These asteroids are rocky and metallic. They range in size from small pebbles to objects hundreds of kilometers across. Sometimes these asteroids are nudged out of their orbits. They can collide with planets and moons, leaving behind craters. Our solar system today is a fascinating place, teeming with a variety of celestial bodies that each play a unique role in the cosmic dance. It's a family of objects bound together by the sun's gravity, creating a harmonious yet complex system. The inner solar system is home to the rocky planets, Mercury, Venus, Earth, and Mars. These planets are characterized by their solid, dense surfaces, and are often referred to as the terrestrial planets. These planets are small and dense, with surfaces that tell stories of volcanic activity, craters, and tectonic movements. They have solid surfaces and thin atmospheres which vary greatly from one planet to another. For instance, Mars has a thin atmosphere composed mostly of carbon dioxide, while Venus has a thick, toxic atmosphere. Earth is the only planet in our solar system known to support life, thanks to its unique atmosphere and abundant water resources. The outer solar system is dominated by the giant planets, Jupiter, Saturn, Uranus, and Neptune. These planets are often referred to as the gas giants and ice giants. These planets are much larger than the inner planets, with diameters that dwarf those of the terrestrial planets. They are made mostly of gas and ice, lacking the solid surfaces that characterize the inner planets. They have no solid surfaces, instead featuring thick atmospheres composed of hydrogen, helium, and other gases. They are surrounded by rings and many moons, each adding to the complexity and beauty of these distant worlds. Saturn's rings, for example, are made of ice and rock particles, creating a stunning visual spectacle. Beyond the giant planets lies the Kuiper Belt, a region of icy bodies similar to the asteroid belt but much larger. This area is home to dwarf planets like Pluto and countless other icy objects. And even farther out is the Oort cloud, a vast, spherical shell of icy bodies that is thought to be the source of long-period comets. This distant region marks the outermost boundary of our solar system. Our solar system is a dynamic and ever-changing place with planets and other celestial bodies constantly moving and evolving over time. But it's also a place of incredible beauty and wonder, offering endless opportunities for exploration and discovery. From the fiery surface of the sun to the icy edges of the Oort cloud, our solar system is a testament to the marvels of the universe.